So the divergence theorem, let me go ahead and write this out. Maybe it's not immediately obvious to you why this surface integral over this closed surface is going to equal this triple integral of the divergence of f. But hopefully I can just help you to understand this intuitively a little bit, because I hope that you'll find that intuitively understanding this is actually a bit easier than understanding Stokes theorem. It's, I think, pretty straightforward intuitively. Before I kind of jump into either one of these, let me just kind of draw out a region E, or in this region enclosed by S on the side, and then we'll get started. All right, so hopefully you can see these are sort of cube, three-dimensional volume type shapes. And on the left, we're just going to think of this three-dimensional volume here as E, the volume contained by sort of these lines in 3 space here. So we'll call this E. Over here, the same cube, but we're going to call this S. And you can kind of think of these a little bit differently. I mean, ultimately, we're taking a surface integral on the F side, so we're going to be kind of looking at like little chunks of the surface like this. Whereas on this side, we're looking at a triple integral, so we're kind of in dv, so we're looking at like this dv is like these little cubes that we're looking at. Okay, so this is kind of the basic types of structures of these two different integrals here. And now to understand this, maybe thinking of this in terms of liquid flow of water in particular might be somewhat intuitive. So let's consider that inside both of these cubes, we've got this source here. And let's say it's within this box, this little dv cube here. I've got this source of water in here, and that water is going to be, emanating in all directions out of my little cube here. So it's like you got like a hose or like a faucet or something that's just emanating water right here. And let's just say for this case that's all that we have inside of this cube. You've just got this water source. Now if I wanted to look at this particular source right here, let's just call it a source. At that source, if I found the divergence of it, that's going to be greater than 0. And of course it's greater than 0 because it's that outward flux from the point, and that's what divergence really is. It's a flux density. So if we were to think of this in terms of units, for example, it's a flux density in three space. So it's going to be in this case, say, liters of water per centimeter cubed or volume. That might be the type of units we'd see for the divergence of our vector field F. So you could imagine this integral sort of sums up all these little cubes in here across this whole region, and it gives you like the total of adding up the divergence of all these little dv cubes. So if we did it in this case, I've just got one source. So essentially, I'm just be finding this total in here will just be that whatever the divergence is at this area. But of course, I'm going to integrate it over 3 dimensions. So I'm going to end up with a number of liters. Not liters per centimeter cube, because I'm integrating in 3 space. It's going to be just the liters. So if I integrated this whole thing, in this case, it's going to give me this positive value, because I've just got one source. And let me go ahead and write down that definition of what this integral would give us. So that would be the total liters of water that are emanating from this region E. That's what this integral, triple integral, would give us. Okay, so now let's take a look at this left side here. But a better way to write this would probably be, that it might help understand it a little bit better. Let's just make a different form of it here. So you may be familiar with this different form of writing the surface integral, where this ds was a vector, and we just kind of made that a scalar, and then that's where this normal vector term comes into play. And then what that normal vector would be for these surfaces, for example, here, it's going to be just this. So you get the idea. That's the normal vector. And what do you imagine if we've got that same sort of cube in here, or that same like source in here, you can imagine that water is actually going to be flowing out of all these sides too. So it would be the water vector might look like this. It's going to be flowing out the top here. It's going to be coming out this way. So you can imagine that this, the water flow, which we're representing by this vector field F, is going to be going the same direction as our normal vector. So you may imagine that our F dot n is going to be greater than 0. So this inside part of our integral is going to be greater than 0, just like our inside was over here, because we had that positive divergence of f. So you can see in both cases we're going to end up with this positive integral because we have a source in the middle. And if we wanted to just kind of say write down what this integral means, you could say maybe it's going to be the total flux flowing outwardly through our surface S. So hopefully you see that this equality here does hold, because the total flux of water flowing outwardly through our surface S is the same as the total liters of water emanating from region E. So this is a basic intuition behind it, but maybe it might help to just add a little bit of complexity to our example here to get an appreciation of how things balance out. So let's just say we had another cube here, and we'll say it's kind of a little bit on the other side of this region here, just to help out. And we'll say like this is actually going to be a drain, so it's going to be taking water in. And for this drain, we could say that our divergence of F at that drain is going to be less than 0. So you could imagine in this case, if I summed up all of the cubes in here, I'd have these two. I'd have this one drain and this one drain and this one source here, and maybe if they're the same magnitude, maybe they cancel out, and my right side of this equation ends up being 0 because these cancel out. So you can imagine that in that same situation over here, if I've got that drain sort of in this corner, maybe my vector this over here, maybe it's going this way, maybe my flow vector is going that way, maybe my flow vector from the back is coming this way. And so in that case, you can imagine what your F dot n might be for this side over here. Well, now that's going to be less than 0 because these vectors are going in the opposite direction of my normal vector, so that's going to be negative. Whereas over here, maybe it's still positive because we had that source kind of on this side. But you can imagine the similar thing is going to happen over here. If we've got a drain and a source of equal magnitude, they're going to cancel out when we add up that flow going through all these different surfaces. And on this side, we're also going to get 0 here. So that's kind of, kind of maybe one step more complicated of an example of how the left and the right side equal each other. And really that's it. I mean, that's really the basic intuition of this. Again, it's not like a rigorous proof. It's just sort of a understanding where this theorem comes from. And hopefully you find it's a bit easier to understand than Stokes' theorem. But let's just go ahead and write out Stokes' theorem too, just to give a little bit of a comparison and contrast, because sometimes that just helps scaffold your understanding of the different theorems. So Stokes' theorem. Okay, so if you recall, this is Stokes' theorem, but just to compare these two, you can see on this left side we've got this closed surface integral, but here we've got a closed line integral. But in both cases they're closed. Another similarity you see is that we're dealing with this this force vector F in both of these, so that's sort of a commonality here. But probably one of the major differences you'll see is that this has the divergence theorem looks at the divergence of F, whereas the Stokes theorem, you need the curl of F. And also you can see this divergence theorem is sort of done at a higher dimension, whereas we've got this double closed surface integral up here. For Stokes theorem, we've got only a single line integral, and we've got a triple volume integral here, whereas with Stokes theorem, we just had a double surface integral. So those are kind of some of the major similarities and differences. But I don't know, sometimes just looking at those can help compartmentalize the different theorems out there. But in general, I hope this was helpful in getting an intuitive understanding of the divergence theorem. And until next time, take care.
Countdown to the scientists.